wants to start. Thank you. A couple of things. We will. I had a prior recording, but I listened to it, and I'm going to try to. I'm going to redo the recording because I've modified the exam, and I didn't really think I had was as expressive as I should have been for it. So I'm going to, if I can't get to that tonight, but I'm depending on how things are going, most likely tomorrow morning I will get that, YouTube it, and send it to all of you as an embedded YouTube for the exam, which will be a week from Monday. So we'll get everything. We should have everything done for the exam by Friday. Okay. So I'll get that review recording and questions, anything. Feel free. I think we're babysitting again on the weekend. Ugh. All right. And so what I did, the other note is I added this particular PowerPoint. Let me get to where I was. Get rid of this silly thing. That is, when we look at all these things, why am I doing this the wrong way? I must drive myself nuts. Why is it upside down? Did I do something silly? Oh, we did. Oh, this thing. And I'm using because I like the illustrations. That's from Nestor. That's this chapter 4. It's really the same content as what we're going to be working on with the chapter 6, this one. And this is the one we'll be using. I'm only going to, in the interest of, there's a lot of material in there that we either go over again or it's just overly explaining like where oxygen comes from, where sodium comes from. I mean, if you want to be extraordinarily thorough, that's things to do. Maybe environmental sciencely, from an environmental science perspective, that's taught. My colleague, Dr. Maurer, who some of you might have for like A&P2. Don't you have Dr. Maurer, some of you? For his course, because he's teaching in micro section. He does the environmental science, and the bio majors micro as well. But nevertheless, so, I mean, I'm going to use this and I'm going to, sort of pick and choose. So this is the one we'll be using, and this is where we begin. And you're going to see, I will make an endeavor to abbreviate it. This is basically how they grow, for lack of a better way. And you're going to see I'm going to, basically the topics that are critical are going to be about air usage, temperature, pH, and at the very end, something that's really important called the bacterial growth curve. And that's something that explains a lot of stuff that goes on in lab, but has a lot of relevance to the insight we draw about how, not only how they grow, but how we attack these things. Very, very much so. So it's really sort of the frame for today. And they talk about, they use terminology I don't, macro and micronutrients. As you will see, and the ones that's important is essential. Again, essential means must be acquired by diet. You learned about that when we talked about essential amino acids in AP1 or essential fatty acids. Essential means must be acquired through diet. That's all it means. So, but really, when it comes to this is the most important acronym is right here. In our cells, periodic table up there, I mean, heck, in the middle of the test, you want to go up and look at it, I'm fine with that. Carbon, hydrogen, oxygen, nitrogen, okay, are the big 4. Remember we learned about those? In us, it's calcium and phosphorus. Because with all the calcium that plays such a pivotal role in our bodies, all the stuff we talked about, you're going to learn more about it now in AP2, many of you. So calcium being stored extensively in bone and mostly traveling around as calcium phosphate. But in microorganisms, carbon, hydrogen, oxygen, nitrogen, phosphorus, and the big S, sulfur, those are all their atomic ones. So remember the difference. That's a test question. Which ones are the important, with the critical elements? 70% water like us, organic compounds, the vast majority. And then they go through, and you can see we don't need a whole lot. In lab, why do people say, why do we use E. coli so much? Like for genetic engineering. E. coli, you need water, sugar, and glucose, specifically sugar, and about 6 different salts, regular salt and some other salts like calcium chloride, those kinds of things. And it'll grow forever. It'll grow continuously. So we use these because they don't need they only need a very, very limited amount of nutrients and sources for the inorganic things to grow extensively. That's the best way to look at it. That's a lab-oriented thing, and you'll probably see that. I'm sure you'll delve into that in lab when you start looking at some of the media and some of the broth and some of the plates that you will use. And so you don't have to worry about any of these things. I mean, to a certain extent, we covered a lot of this. Many of us in AP1, we talked about minerals, which is basically the trace elements and stuff. So I'm not really interested in macro or micronutrients. The only thing that interests me here are these first two. For our purposes, there are a lot of exotic kinds of microorganisms that really aren't relevant to this course, I feel. An autotroph, self-troph growth, that has to have chlorophyll. The only examples we really deal with in the microbial world are algae. And so what they do, they use the sun, solar energy as their energy source, and they fix carbon. They have carbon dioxide and water. And the carbon dioxide, they affix or staple the carbons together to basically make the things they grow with. So they're able to grow by themselves. The sun provides the energy, the carbon dioxide and the water provides all the stuff that they need. So plants and algae, by definition, as long as they have chlorophyll, are autotrophs. Are there photosynthetic bacteria? For sure. But they really are not something, they're more exotic and we don't really work with them. We, the E. coli, the yeast, the staphylococcus, that you work with in the lab or that are in our environment, are heterotrophs. Hetero means many. And so we use a lot, and specifically we're called organochemotrophic. We all do, and so do the bacteria. We gobble up organic chemicals. What do we eat? We eat carbs and fats and proteins, things that we can utilize to make nucleotides. We have water. We have trace other elements we use, vitamins and minerals, etc. Those are all effectively, other than the trace elements and the salts that we utilize, are all organic compounds. And we gobble them up and we break them apart for energy. And we frequently use, when we break them up, as building blocks for something else. We went over all this in AP1. So we are heterotrophs, or organo, or if you want to be technical, chemoorgano, because they're organic chemicals, heterotrophs. And so I'm not using these charts. I don't want you to sit there and look at this or look in the chapter and go crazy. Like here, this one relies on inorganic materials, requires neither sunlight or organic nutrient. Chemicals from stone. Litho means stone. Oh, I had a very tasty rock today. Oh, very good. Now, I don't know any, right? I don't eat rocks. The occasional pebble. See, I could go into all this, like leaving no stone unturned. Go ahead. Stop the madness now. Many of you are going, what is wrong with him? It's okay. We'll see a little bit at the very end. And if we get to it today, we got to it in the other class at the very end, we'll talk a little bit about parasites. We do so much of it now, so much of it throughout the course. A parasite, the implication is bad. It uses you or stuff on you or in you to grow and hurt you, and it thrives. That's really what a parasite is. And we're going to go over that definition many, many times when we start talking about relationships between us and microorganisms, ones that help us and one that hurt us. Sort of by definition, parasites that hurt us in certain ways, we've used the term pathogen because they cause damage to tissues or even death. So some parasites, in this context, we're talking about some parasites we can live with, but I'll show you really a better description later. And we'll revisit that when we talk about how diseases spread. And there's, all manner of microorganisms, whether they're on the body, on your skin, lining cells, or inside of you within organs or tissues. We'll address that, what it is. And we'll talk about intracellular parasites. And some that have to live there. As we will get to viruses, they have to live inside of a cell. And live is the wrong term. They have to replicate inside of a cell. The plague is an intracellular parasite. as you can see here, other ones of these syphilis inside cells, leprosy inside cells. And we'll get to those. You don't have to know those terms at this point. They're more for context. When we get to the specific way those diseases affect us, we'll deal with it. And they have a whole thing about where do you get the nitrogen and where you get the phosphate and the sulfur, and no thanks. And what the other things they do, fine. You can look at that. Bless you, all sneezers. This is review. Okay, this is part of that. It's a prerequisite. There's some subtle differences when it comes to movement across membranes. Remember, active transport involves energy. We use the term pump. We have to move it either against the concentration gradient. So the driving force for diffusion or for facilitated diffusion, concentration gradient. Down the road, I told the other class, when you get to AP2 and you start talking about respiratory, you're going to see solubility moving through a membrane plays a role. Okay, that's another factor that's there. But concentration gradient is it doesn't matter whether it's water, osmosis, whether it's oxygen or carbon dioxide, whatever chemical it is or whatever gas it is, it's effectively concentration gradient. So diffusion, okay, moves along the concentration gradient, and I don't want to go over these. We know the difference. So remember the terms, I use the term solute, stuff dissolved in the water, or solvent for water. Okay, we're dealing with living systems here, and viruses don't really do business this way. So the solvent, universally speaking, in living things is water, certainly, that we are aware of. So again, selectively permeable membrane, all this stuff, you can read it as easily as I can read it to you. And they show you some examples. We've seen all of these things that effectively, this is relevant because it's different between, and this underscores the difference between our cells, or a microbial representation of our cell would be a protozoan like an amoeba, versus a bacterial cell which has a cell wall. And back, you might recall me mentioning this to many of you in AP1, this was the distinction between plants and animal cells. And they're different. And it's really significant going forward in how we address them, because controlling water, either moving water in or moving water out, because water is essential for life, plays a pivotal role, as you will see when we start thinking about controlling certain kinds of microorganisms we want to get rid of or stop from growing. So that's where we look at how they grow with the long-term goal of how do we control the growth if it's something that's undesirable, or how do we facilitate or enable the growth if we want it to grow, right? So here we are. So remember, when it comes to water, we use the term tonicity. Tonicity is this relatively fixed relationship, more or less, in living things, the amount of solute to solvent. It's a ratio. And you in this whole thing, we might remember we talked about things like milliosmoles. I wasn't going to ask you about that. But inside of our cells, in between our tissues, extracellular fluid, intracellular fluid, plasma, cerebrospinal fluid, more or less it all has the same tonicity. And so if we take a bacteria, or we take one of our cells, or we take an amoeba, protozoan cells, and we put it in an isotonic media like normal saline, the one you deal with most commonly, because one normal actually by definition means isotonic. It has that same milliosmoles number. Water will move until it reaches equilibrium, but it's not going to move more in or more out. It reaches an equilibrium with a steady state because it's a living thing. It's always moving in and always moving out. Think dynamic when you think living things. When you're starting to talk about any kind of biology, living things, you got to think stuff on the move all the time. So water is neither going to move in or out excessively. It's going to balance out. That's really a significant thing. Now, hypotonic. This was a red blood cell in us. Or if we had amoeba that we wanted to get rid of for some reason, and we put pure water, triple distilled water, triple deionized water, pure water, with everything is moved as much as we possibly could, water would be forced into the cell. You might have recall seeing this slide when we talked about a little bit about hypotonic things that meant they had a very, very large amount of water and very, very little, if any, solute. And what happened? It would worsen so fast the cell would burst. I said, and the only way you can see it in a red blood cell if you're watching it in real time. If you had a microscope and a continuous camera, or you basically a continuous feed that you could see because it bursts almost instantaneously. That does not affect bacteria with a cell wall. They're very much like plants. We thought they were little plants. So what happens when you water a plant? It doesn't. Okay, one, it has things in it like vacuoles. It can pump out extra water. But effectively, in a bacteria, it just pushes the plasma membrane against the cell wall and really has no adverse effect. The cell wall keeps it intact. So when we think of when we wash our hands, we're not killing any bacteria. The mechanical action of the hand washing and the flow of the water washes it away. Even when we use soap or something like that, effectively it just enables that a little bit more because there's a lot of bacteria in dirt and grime, and that substance is basically will dissolve the dirt and the grime in one end, and it'll be water soluble in the other. That's how soaps work. Okay, whether it's laundry soap or hand soap. So you're not getting anything special out of that whatsoever. I do a lab, and you may do the same lab, where we do a hand washing lab, and I used to do it with special soaps and regular soap or no soap or betadine and all that type of stuff. And frankly, they're all about the same. That's why hand washing is so important. So the bacteria with a cell wall, or any organism with a cell wall, will go, okay, water me, make my day. So you can't overwater. But the big player here is hypertonic. Think salt water. Think just salt. And what happens is, and these are the names you might remember. So if we do it in like a red blood cell, it kind of shrivels and it disrupts. The fancy name we give to that is called crenation. So that's in with no cell wall. Kind of shrivels. And what happens here in a bacteria with a cell wall, remember it's an envelope. If we pull the membrane away from the cell wall, the plasma membrane bursts and basically the cell dies. The fancy name we give for that is plasmolysis. Lysis means to burst or to split. Plasma means the plasma or cell membrane. Important words. That's why we salt things. The original preservation was salt. We salt things today. A lot of traditional foods that are coveted in the gourmet and the cooking world, salt cod called bacalhau. Okay, very common in Portuguese and Mediterranean cuisine. The best capers come packed in salt. The best sardines, anchovies, all get packed in salt. Not the oil we're so used to, or brine that we're so used to. And you got to rinse it off and do that stuff. It's a little cooking tip. Caesar salad wouldn't be the same without those anchovies. And that wonderful lemon and caper burst for like veal or chicken piccata. Okay, so you don't like to eat. It's all right. You're talking to somebody, oh, my wife, do you really want to have burgers again? Yeah, works for me. I may talk fancy, but it's more simple. Not a whole lot here. This is all review. Active transport, energy, blah, 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 blah. Okay, endocytosis, exocytosis, penocytosis, energy. I mean, all these oddball things. So we're done. Temperature. Now we get to the important part. I'm going to check my time. Good. So that's the background stuff. Temperature. Okay, I'll give you the first example. Something to know that isn't temperature, but just to make a point. Okay, if we look at cells, if we look at typically something like pH, going from 0 to 14, and we look at growth, we talk about the optimal pH. For us, you might remember about 7.4 plus or minus 7.35, 7.45, that would be here. And so if we lower it or we raise it along the pH scale, remember 0 to 14, it kind of looks like that. Everybody knows that kind of curve. It's a bell curve because it's like a bell. It's got a fancy name, normal distribution, Gaussian distribution, whatever. And actually, we'll talk about it a little bit as time goes on. And so the pH classification that most of the things that impact us in the microbial world is roughly from pH 6 to 8. The name we give them is called neutral because it's relatively a neutral pH. Bile, which means they like it. The E is very important. The most common white blood cell in our body, for those of you taking AP2 when you get to the blood, is called a neutrophil. No E. If it looks like that, I wouldn't put it on a test. Somebody might. It's like you know, everybody knows this. If you haven't had me before, you should be aware of it. If you can come up and ask me if it's at a misprint or whatever, sometimes I'll certainly tell you and share it with everybody. Sometimes you'll come up and say, I can't give you more information. That is a luxury you do not have with other teachers. Not all. Some do, some don't. Because I would rather you understand it. I have enough tricks in my sleeve, I know. A, B, could be C, might have been D yesterday, but it's E today. Only for a short time. If you act quickly, the credit card with 4 equal payments of $1,000, it can be whatever answer you want. C number 2. I don't like it. Temperature is different. Yeah. Temperature is not a bell curve. Can you kill something by altering its pH? For sure. Okay, but it's equal directions. If you lower it or if you raise it, it will follow the growth of that bell curve. Temperature doesn't do that. When it comes to temperature, from 0 all the way to whatever, okay, and you look at growth over here on the y-axis, effectively we have what's called T optimal. Q and I, that's 37 degrees Celsius, good old 98.6, the old Fahrenheit scale, right? That's here. And then we have to concern ourselves with lethal temp. T, and so this part of the curve going down looks normal. This part of the curve, like falling off a cliff. The lethal temperature for us, just to give you some context, if it's 40 degrees Celsius, okay, 40 degrees, which is not the lethal temperature, but could be depending on circumstances, is about 104. If you get up to 42, that's 107.6 Fahrenheit. You're going to die. That's almost irreversible hyperthermia. The T lethal is not here. The T lethal not going down because cooling or even freezing something doesn't kill it. We've seen that. Even when you're thinking on a cellular basis. Okay? The fact that you freeze something and you bring it back to room temperature doesn't allow you to eat something that potentially would have hazardous bacteria. It does not. They're still there. You still have to cook it. Okay? Why this occurs and why they are so close and why it's like falling off a cliff is critical because we use heat more than anything else in our environment to take care of bad microbes in our environment. We sterilize. We superheat something to kill them. We boil things. It doesn't necessarily sterilize them. We cook things. And what this means when it's like this, when it dies, irreversible. Big name, because what happens once it hits T lethal for a sufficient amount of time, proteins denature. And as you remember, when you denature a protein, it's irreversible. Got it? I want my steak, my meat, your steak comes too, this is too well done. When you make it less rare, it doesn't work in that direction. Right? There's a zillion analogies for that. You can't uncook it. You can't unscramble it. You can't do that. because it's irreversibly denatured. That's what temperature does. And that's why it's so critical to understand that. That's a really critical piece here. So we have a minimum, a maximum, and an optimum temperature. This is why I tend to use the other PowerPoint just a little bit to emphasize the point that's here, because it doesn't show it as well. Here's what theirs looks like. And they have different classifications very concisely. The other PowerPoint kind of drones on like me. So the optimal growth is usually close to the upper end of the range. T optimal is close to T lethal. The category that impacts us the most, the disease-causing organisms, is right around where we grow, 35 to 40 degrees Celsius. Our bodies are 37 degrees Celsius, 98.6. So that's where they do best. We call them mesophiles, files because they like it, meso because it's in the middle. And it's usually, the range is typically 25 to 45. There are some that like it a little colder. Leprosy, for instance, likes to go toward the lower end of that and grows a little better. That's why it tends to affect noses and ears and fingers and toes, because we call those acral, acral areas, because the temperature, the skin temperature in those areas diminishes compared to central. All of these are, what I'm sharing with you are factors. Why we look, why when we're trying, if somebody says, why would this not be something? These are all the little things that if you really want to be good at what you're doing, you need to learn. Not to remember it, or you can look it up and all those kinds of things. But I'm trying to give you, to share some of this with you. I've seen one case of leprosy. But mostly are mesophiles. These other two categories, thermophiles, they like it warmer, or psychrophiles, not psycho, psychro with an R, like it colder. These are the three categories that impact us, happy cursor, and the overlap a little bit. I mean, okay, thermophiles start at 45. There's some that start lower. Mesophiles, there's some that are a little higher. Okay, so there is always a degree of overlap. So hot springs, compost heaps, if you use compost, we have one of those spinny composters in the back that we use, like we use it for plants and fertilizer, that kind of stuff. It generates a fair amount of heat. Where does that impact us? I'm sure you're not going out and composting yourself. You're putting that stuff on your arms and stuff like that. And people but in our environment, not just hot springs, but hot tubs. Hot tubs are interesting. We're going to see a lot of times there's organisms that get in when you get into a hot tub that's not properly dealt with from a disinfection standpoint. I mean, the same thing if you have pools are a pain in the neck. Above ground pools, in ground pools, hot tubs in your home, whether they're inside or outside, you got to be on top of that. Like yesterday, we managed to get all that more than a foot of snow we had on our big deck, and we have a small hot tub that's sunk into it. And the first thing we did when we finally could access it, we got bleach in there. I mean, it's so easy to do. You have all these little indicator things, you know what to add. There's nothing to it. But that's stuff you need to do. And it's greater still. And down the road, we'll talk more about when you have these shared ones in facilities, like if you go to a gym or a health spa that has that, or a hotel, that type of thing. Got to be, and then ventilation plays a role as well. And there's some interesting diseases that are associated with it. So they're part of. We have to deal with them because we run into them more commonly now in our environment. More coming on that. So mesophiles for sure, thermophiles, not extraordinary, and certainly psychrotrophs means grow well in cold. Spoilage organisms. They're always there. When you refrigerate, when you cool it, you don't kill it, you slow down its metabolism. When you freeze it, temporarily you may stop its metabolism. Freezers, you really don't see bacteria. That's sort of a misconception that it's rare that bacteria grow. A freezer burn used to be, that must be bacteria or something else. No, it usually has to do with mishandling things you put into the freezer. Most of us do it. I'm guilty about this unless I'm doing something fancy, is You just shove it in a zip top bag and toss it, right? Not good. This freezer, yeah, you're guilty. I can see that. Do you label it and date it? I think not, even though you're supposed to. I don't either. So the freezer police come to see me once in a while. Look, my wife says, "Well, I don't feel like going. Let's see what's in the freezer." Yeah, how many times do you go? What is this? Or more appropriately, what was this? Freezer burn. I'll go into why it's mishandling. So you can learn a lot from watching food shows. So psychrophiles and hyperthermophiles are extremes. Yeah, that's in the freezer. Freezer is certainly at zero. Most refrigerators, yeah, typically you can set them now, probably around 37 to 40 degrees, okay, Fahrenheit. So depending on how cold or how not cold that you want them, but they definitely are important. But these are more archaea, okay. So they're really not. They don't play a role with us. So, and thermophiles is about denaturing and refrigeration. See, typically about 4 degrees Celsius, about right. Okay, slow spoilage, limiting it. Stuff still spoils. Okay, they can still grow, but so slowly. So freezing is a preservative, not effective because when you defrost it, like I said, but here's the leprosy nugget. So I like that graph. That's why I went there. And I like when we're going to use it on Friday when we go over this growth curve, which I think is about the most important thing we can study in this. And you see their graphics are a little bit, they talk about this and they go into all of those. And I agree, they're really interesting. Staph can grow in your fridge. When we see problems with food poisoning with dairy, it's usually Staphylococcus aureus. And it's usually for dairy that was probably in the fridge a little too long and it hadn't started to get that clump up or get that characteristic odor, the old, how old does this milk smell? You know who you are. I do the same thing. This is very interesting. And without this PowerPoint or this book, Listeria, if you do not know what you should do, let me rephrase it this way. Whenever you see an article in the paper or online or any website about a recall, I get them on what's called all recipes, all the recalls. See what the bad guy is. Listeria monocytogenes is extraordinarily dangerous in compromised people, particularly not just people with cancer and are immunosuppressed, pregnant women. And every so often you get, and they can be fatal frequently. There was a outbreak some years ago in the exterior of cantaloupe. Basically it's in the soil and it comes from fecal contamination from animals where it grows inside normally. And what people will do, they get it in the store. If you're lucky, they wipe it off. And most people don't. Well, it looks pretty clean. And they get out a knife, and the knife brings down whatever outside, inside. If it's Listeria, you're in trouble. There's nothing in the flesh within is sterile, okay, of that particular thing. It's not, you don't have to do anything with that. You just eat it right away along with that. I don't know. Look, I tell everybody, you all look at me strange. I mean, if nothing else from that anecdote alone, you should be washing all your fruits. And when it comes to those things with those hard rinds, you probably need to scrub them. I'm not saying soap and water, but water and get one of those nice non-damaging scrub brushes that are soft and spongy, and get some of that stuff off of there. I use this anecdote as well. College students, it's very easy in a dorm room where you're not supposed to cook, and it's easy. You can go to the store, you get little bags of salad, say pre-washed. You can buy little veggies and stuff like that. Did you see them wash that? I didn't. Get a little colander and wash it. Or my favorite tool, a salad spinner. Everybody see what one of those are? You put them in there. It's like a little colander. You put it in, and the water goes off with centripetal force. Love that. And it's better because the dressing adheres better to salads that way. Pros use that. It's sort of the dressing then adheres, embraces. So here, medically significant, yeah. Thermoduric are ones that can survive, don't care. These, now endospores are a problem. as we'll get to. And I mean, this is one of the difficult things. We have to be very watchful about potential endospores. And you'll see what we do. That's when we get to sterilization. Thermophiles, a lot of different places that are there. Typically, when they get above, and that's when we start getting to Pasteur, that's why his holding and use of pasteurization, which we deal with in the next chapter. The next chapter we do, which is not on the test. Basically, this is how they grow. This is how we kill it or control it. There's their temperature file. It's not quite as distinct. Some of these are a little more. I mean, they're not quite. I like the dramatic falling off the cliff. These aren't bad. And gases, we know about this. These are oxygen levels, and oxygen levels are important. I must tell you that. So if I go back to the other PowerPoint, there are 5 levels when it comes to oxygen. Okay? And basically, these are the 5 things. It's based on oxygen requirements. You and I are obligate aerobes. If there's no air, if we're without air, what? 6 minutes, we probably die. If we go brain dead, and then you're dead. Based on the legal definition. Obligate aerobes, we must have oxygen. You're going to see facultative aerobes, okay, use oxygen but don't require it. The word facultative is important. Facultative means that you have the faculty or the capacity or the ability to do something. So a facultative aerobe can grow anaerobically. For instance, E. coli, interestingly, is a facultative aerobe. It can grow in air. When you cultivate E. coli in the lab on your plates, it's growing in an aerobic environment. But what it does is the air starts to go away, and sitting with that plastic thing on top of the plate over the time, and the air is gobbled up, it is able to grow anaerobically because it undergoes a process called fermentation. So tell me, when you open up that incubator in the lab, doesn't it start to smell a little funky in there? That's fermentation. And it's only going to get worse for the term. So most of the stuff we utilize, almost all of those gram negatives that you'll be testing, E. coli and Proteus, okay, you're going to find Enterobacter aerogenes. All of those will be facultative aerobes. We find them in our gut. Our gut is effectively, our colon is an anaerobic environment, but they can survive in the air as well. And it's all because, remember last time I talked about superoxide dismutase and catalase? It's all because they have varying amounts. Sometimes they don't have them at all. The ones that don't have them at all are here, obligate anaerobes. Not only can't they use oxygen, they're destroyed by oxygen. Interestingly, microaerophiles, too much air. It's again, the heart of this discussion is that certain things can't deal with toxic derivatives of oxygen. Oxygen produces free radicals in any environment with nearly any organism that has to use them at all. So microaerophiles really are only useful with either remember our oxygen that we're inhaling now is about 20% of our atmosphere. They have to be between maybe as little as 5% and as much as 10% oxygen, maybe even a little bit lower. That is, so if they're in regular air, it's bad for them. You'll see the way they grow shortly. You're going to see the way the tubes look with this in the experiment. Now, I've done it in other schools. We don't happen to do it in this one. It requires a special media that's there. And so microaerophiles are very significant in disease. One, and this is again, I take issue with it, but it is true that Helicobacter pylori, which is associated certainly with gastric cancer, and some people believe, though I am not a subscriber to that it plays a role in gastric ulcers. That's a microaerophile. The other one is a variation of Streptococcus pyogenes. Streptococcus pyogenes is not in this category per se. There's a particular variant, and what it causes is something you hear about. They make a big deal about in the media, but the reality is there's probably less than Sure, less than 50 cases in the United States a year. It produces something called necrotizing fasciitis. Fasciitis. Look it up. And it's known as the flesh-eating bacteria. It's not the only one. It's by far and away the most common. It happens in low oxygen environments. It is relatively rare. I have seen 2 cases in my clinical career over a 25-year span, 2. That's a lot. That kind of rare. One was in a diabetic. Diabetics have bad circulation in their legs. The other was in an IV drug user from damage because it was probably injected, and because of the damage from multiple injections, it probably limited. You're lucky if you get away from an amputation. You get away with an amputation. Lucky. I'll go in. We do it with wound infections. I'll talk about it. Interestingly, when we get to wound infections, the people we worry about the most are people who inject themselves not aseptically. And that's which, like a lot of times, bodybuilding, steroids, locker rooms, bathrooms, big problem. That's the big area. If you're watchers of The Pit, that great show on HBO, that was the diagnosis in the episode they just had, the most recent episode. I had it. I told my wife as soon as this gal walked in, I said, it's going to be neck fascia. How'd you know that? Because I saw it as a resident. I had a patient with it. When you see things, remember them. Oh, not done yet. Backing up. And so you see the tubes that are there. Aerotolerant, they don't need oxygen. They don't use it. But because of oxygen around, they have to be able to deal with it. So we call them obligate fermenters. Fermentation, bacteria don't have, you and I have energy. We have to think. We have to interact aggressively with our environment. You have to look at things. You have to, all that stuff, using energy constantly. Bacteria basically reproduce. So they don't have to do that 36 to 38 ATPs with aerobic respiration. Fermentation makes a couple of ATPs. It's fine. So those are the categories. And here's why I like this PowerPoint. Obligate aerobes only grow when oxygen is available, require it. They have both the superoxide dismutase and the catalase. Facultative, produce both. Use oxygen if available, if not, they ferment. Anaerobes don't use it. So things like all those tetanus and botulism, and there's an error on the other PowerPoint about that. They don't produce it. If it's there, if they get exposed to oxygen, and we do this intentionally. It's like a diver with the bends, when we'll probably talk about that in AP2 with respiratory and blood gases, they put them in a hyperbaric chamber, but they use compressed air. We put oxygen, we call it hyperbaric oxygen. It's been around for a long time. Burn units have it a lot that are useful because you got to force oxygen because of carbon monoxide inhalation. And so, I have a fair amount of knowledge about that. And I've seen it used in different fashions, and something I typically address. So if you're interested in it or seeing it in AP2, give me, like I said, with AP2, if you have some questions or stuff, you just want my spin on it, email. Obligate anaerobes, they don't make it. Microaerophiles produce some. That's the problem. And then aerotolerant produce superoxide, but not catalase. In lab, you're going to do a thing called the catalase test. And that's all because of these reactive oxygen species. We did the pH. I should talk about this if nothing else. Okay, what Staphylococcus is it likes salt. It's tolerant up to 10%. When Staphylococcus grows on our skin. In the lab, in a couple of, maybe next week or the week after, you're going to use what are called selective and differential plates. One of them is called MSA. It's kind of reddish. If Staph aureus is growing on it, and there's other kinds of Staphylococcus, it will turn yellow. Why it grows there, and when we test for MRSA in the hospital, we use this media because it's like your staph grows on your skin. It's salty. So we use 7% salt. That makes it selective. So the Staphylococcus, it will favor their growth. And we add another chemical in there with a dye because of pH variation, and it'll cause a color change. That's what you do a lot. You're going to see a lot of color changes in the way we analyze what bacteria is which. That's part of the lab that you're in that are there. This is the major and minor elements. I'm almost done. I know you're getting antsy. I don't blame you. I don't want to listen to me that much anyway. And they had a few things in here. This was the oxygen and some of the stuff. Here's the hell. That's Lyme disease, by the way, a microaerophile, which I was unfamiliar with. Tuberculosis grows in your lungs. You can understand why. Use the oxygen. Staph, I feel, is more aerobic, and I don't. Maybe there are strains that are part of this. I don't necessarily agree with that. Obligate anaerobes. I mean, oral bacteria are sort of unique in that regard. Intestinal bacteria, certainly, there are obligate anaerobes in there. And see, Clostridial species, Streptococci, I'll buy. Okay, but Clostridial species, I'm not so sure. I mean, to me, they're obligate anaerobes. I mean, I hate to disagree. And you can see the tubes, and that's when you start to grow stuff in tubes. You're going to see that. You're going to see that with B sub, Bacillus subtilis, it's going to grow at the top of the tube. We don't really see the microaerophiles, but facultative anaerobes and aerotolerant will grow all through a tube when you inoculate it. And we don't deal with strict anaerobes. It's a special, you have to put this in a special broth and treat it in a certain way. Here's the pH. Now, radiation we're going to cover subsequently. Pressure we'll cover subsequently. So we'll stop it here. All right? Rather than rush through it. I'll finish what's left of this chapter, and that'll conclude the test material on Friday for those that are not traveling for sport. So I already gave Ava a hard time.